In lecture 5, we'll talk about some performance metrics for classification problems. So we have talked about some simple classification methods, for example, the logistic regression for binary classifier, and also softmax regression for multi-class classification. And we also talk about one of the performance metrics for classification, which is the accuracy. And we know the accuracy means the number of labels that the model predicted correctly. And here we actually want to extend our scopes for performance metrics, and we'll see different kinds of performance metrics and why, in what cases we want to use them. So the first one is about the confusion matrix. Right? The confusion matrix actually doesn't give you any metrics, right? It's not a single number. Right? For example, it's not a matrix that gives you like a number that you can use to compare with the other model. Right? So it's itself, the confusion matrix itself is not the performance metric, right? But it's the foundation for generating or defining a lot of other performance metrics. So we need to first get an idea about what confusion matrix is. So here we're talking about binary classification. So suppose we use one example that will help us better to understand different performance metrics. So the example we're going to use is the classification problem. So we want to predict whether a person is having cancer or not. Suppose you have, for example, maybe the X-ray or CT image of a patient, right? And you want to predict based on the image, you want to predict whether the person has cancer or not. And so here this is a binary classification problem. We'll use 1 to represent a person who has cancer and 0 for the person who does not have cancer. And here we define the confusion matrix. And here we have 2 dimensions here. One, you look at the columns. The columns are about actual cases. For example, the first one, you write it as positive. This means actual positives. So the first column means the patients who actually have cancer. And the second column means the patients who actually don't have cancer. So the column means actual cases, positive cases, actual positive cases, and actual negative cases. And there are 2 rows here. The first row means, for rows, it means predicted cases. For the first row, it means predicted positives. That means your model predicts those patients that predict those patients have cancers. So that's the first row. The second row means the cases where the model predicts those have not cancers. So rows means predicted cases, and columns means actual cases. So now, based on this definition here, we actually have 4 cases here. One is true positive. TP means true positive. Right? So what does true positive mean? So positive, look at all of the second letter here. The second letter means the predicted case. So here, the positive TP, the positive in TP means the patients are predicted positive. That means the model predicts these people or these patients have cancer. And the first letter true, T means true. True positive means the model predicts these patients have cancers, and it predicted correctly. So that's true positive. Right? This is the intersection of predicted positive and actual positive. Actual positive. Right? The model predicts these patients are positive, and they're actually positive. So that's true positive. The second is false positive. Again, the second letter means predicted case. In this case, it means for these cases, the model predicted them, predicted these patients have cancers, but actually they do not have cancers. So it's a false positive. The model predicts positive cases, but actually the model did not predict the cases correctly. So it's false positive. False negative, that means, again, negative means the model predicts these cases as negative. And the false negative means the model predicts these patients are negative, which means not have cancer, but actually they do have cancer. So the model didn't predict these cases correctly, so it's false negative. And the last one is true negative. The model predicts these cases as negative, and also these cases are actually negative. So it's true negative. So true positive, false negative, and true negative. But once you have a model and you have all of these true labels, then you can look at then you can use your model to predict the labels and compare with the true labels. And then you will get this confusion matrix. So right, again, so the definition of TP, TN, FP, FN are here. And for example, look at a particular example. So suppose a person having cancer and the model classifying his case as no cancer. So what we should do, or which of these cases we should use, TPFP or FNTN? So which one we should use? So again, the model classify his case as no cancer, so it's negative. So the last letter should be negative. Did the model predict this case correctly? The person actually has cancer, but the model classify him as no cancer, so it's a false negative. The model didn't predict this case correctly, so it's false negative. All right, so what's the ideal scenario? The ideal scenario is true positive is a certain number, but the false negative is 0. The false positive is also 0. Whatever true positive, true negative, whatever those numbers are. We actually want false negative, false positive, which means the cases where the cases that your model predicted incorrectly, you want this number to be 0. Right? So this is the ideal case. But in real life, you don't have a model works that well. Right? So this will be a number which is greater than 0. This will be a number greater than 0. Right? That's in practice. All right, so if you are, if it's the first time you see the confusion matrix, right, it may take some time for you to understand what these tables are, what this tables is about. And sometimes you will see different columns, right? Maybe negatives, 0 will be the first column, right? 1 will be the second column. Again, 0 will be the first column. 1 will be the, 0 will be the first row. 1 will be the second row. Right? Sometimes you can see actual may be the rows and predicted may be the columns. Right? But whatever, however it changes, right? The meaning doesn't change. All right, so we just mentioned for these two cases, false positive, right, is greater than 0, false negative is also greater than 0. So that's, it brings up the problem. So when you are training the model, do you really want to, for example, reduce the false positive as much as possible, or you want to reduce Fn false negative as much as possible? And so that can be a decision when you're training the model or when you are selecting the model. So it depends on the problem. Right? Sometimes you want to minimize false positive, and sometimes you want to minimize false negative. Right? So here we have two cases corresponding these two different situations. Right? So if we look at the cancer detection problem, right, here we actually want to minimize false negatives. Or false negatives means your model predicts a patient has no cancer, but actually that patient has cancer. So you want to eliminate these cases, or you want to minimize these cases. Right? Because if a patient is diagnosed as having cancer, having no cancer, but actually this patient has cancer, that could be a real problem for this patient, right? Because if he's diagnosed as no cancer, then there will be no further tests, right? Or there will be no further treatments, and the patient will think he's healthy, right? Or it's just some regular disease, and miss the opportunity to cure the cancer. So we don't want to have actually we don't want to have any cases like that. But in general, we want to minimize those false negatives in this case. Right? And also sometimes we in this case, you may also wonder what if we minimize false negative, but we have more false positives, right? But for this particular case, false positive is not really a big problem. False positive in this case means the model predicts the patient has cancer, but actually the patient doesn't have any cancer. In this case, if the patient is diagnosed as having cancer, he will go through further tests, and eventually it will be found that the patient has no cancer, and alarm and remove the alarm. Right? So the false positive is really not a big deal compared to false negatives in this example. And sometimes false positives is more important than false negatives. So we want to reduce false positives. And having more false negatives may not be a problem. Right? This is the case of, or the example of detecting spam emails. Right? In this case, actually we want to minimize false positives. Right? False positives means the model detects or predicts an email is a spam email, but actually it's not a spam email, or maybe it's an important email. So it will put an important email into your spam folder, and you won't see it. And you don't want that many cases like that happen. So you want to minimize the false positives. And you can tolerate increasing false negatives, which means you have more cases where the model predicts the email to be non-spam, but they're actually spam. In this case, you can just look at the spam, read the spam email, and you just delete it by yourself. So people can tolerate more positive negatives, but we cannot lose any important email. So we can tolerate many false positive cases in this case. Right, so there are, based on different problems, then we may want to minimize false negatives or false positives. All right, so based on the confusion matrix, we can define some metrics, right? These metrics are just numbers, right? Which is different from the confusion matrix, which gives us a table. But we can actually use these numbers to compare models. The first metric is accuracy. So we have already talked about accuracy, but what is accuracy? What is indeed accuracy based on the confusion matrix? Right? It's actually true positive plus true negative divided by all of the cases. Right? True positive and true negative, those are the cases where your model predicted correctly. So that's the number of cases that your model predicted correctly. Right? And we divided it by the total number of cases. That's the accuracy. That's the same as what we saw in lecture 4. Right? So so you might think accuracy is just a pretty good one, right? Why do we need other metrics? Right? Accuracy is enough, but actually we can see an example here that shows accuracy is really not very good in many cases. Right? This is especially for the cases where we have skewed data sets. Right? Skewed data sets, right? This is opposite to the balanced data sets. Skewed data sets means one case, for example, spam emails can be a lot more than the non-spam emails, for example, right? Which means some classes are much more frequent than others. Right? For example, if you have 90 spam email and 10 non-spam email, right? That's a skewed data sets. For this case, then accuracy is a not good measure. Right? So we have an example to illustrate this. Right? We look at the cancer detection example. Suppose we have 100 people, that's the total number of cases or instances, and 5 people has cancer. So that means actually 5 people are positive. And we just make up a very bad model, and the model is just predicts every case as no cancer. So this is really bad. It doesn't make sense. Right? Or there's no predictability for this model. Right? Just to label everyone as no cancer. So this is a really bad model. But when we look at the accuracy of this model, so there are 95 people who have no cancer, there are 5 people who have cancer, right? Then what's the accuracy? The model predicts everyone has no cancer. So 95 people are true negative. There's no true positive case because the model doesn't predict positive case. So true negative, in this case, is 95. True positive is 0. So 95 plus 0, that's 95. Divided by the whole, all the cases, that's 100. So that's 95%. And for the accuracy to be 95%, that's pretty good. But actually, you're using a really bad model. So the accuracy in this case doesn't mean anything. It's not good to measure. It's not good metric, right, to judge if a classifier works well or not. Okay, so but you can also use it in like balanced data sets, right? That can provide you useful information, but not for skewed data sets. All right, so since accuracy cannot work for all cases or all problems, then we need to define some other metrics. Right? The first one we look, which is very famous, is called precision. Right? Precision, and the next one is recall. They're both pretty famous when we talk about metrics for classification. So here, the definition of precision is TP divided by TP plus FP. Right? TP is true positive. And TP plus FP is the total number of cases that the model predicted positive. So that's the proportion of true positive to all predicted positives. So it's true positive divided by the sum of the first row. Right, so we use our cancer detection example to illustrate what precision means. It actually tells us what proportion of patients that we diagnosed as having cancer actually had cancer. right? If it's 100%, what it means, if the precision is 100%, that means, for example, you predict 40 people have cancer, and they're all true positive. There's no false positive. That means you predict the positive cases your model predicted are all actual positive. You don't have false positive. You don't have a case where you predict a person is positive, but actually the person is negative. The person has no cancer. So this is about precision. You predict many cases, right? You predicted a certain number of cases that are positive, and all of the cases are true. That means your precision is 100%. If you predict like 50 cases where the patients have cancer, which means positive, right? 49 of the cases are correct. Only one of the cases is incorrect. Then your precision is 49 divided by 50. Okay, so this is what precision means. Right? So the precision is actually decided by false positive. If there's no false positive, that means the precision is 100%. If the false positive is larger, then the precision is smaller. Right? So it's totally decided by false positive. Right? Where the precision is all about false positive. If there are more false positives, then the precision is low. If there are fewer false positives, then the precision is higher. Right, so look at this example again. 100 people, 5 people have cancer, and we use the bad model again, predict every case as cancer. So let's see what's the precision here, right? The true positive is 5, right? So the model is actually different than the previous one. In the previous one, it predicts every case as no cancer. Here, it predicts every case as cancer. Right? So this is actually a pretty bad model, right? But since it predicts every case as cancer, so the denominator here is 100. All of the predicted positive cases, that's 100. And what's the true positive? Since only 5 people have cancer, so true positive is 5. So it's 5 divided by 100. The precision of the model is 5%. Okay, so it's low. It's really low. So the precision can detect this is a bad model. Right, so this is the first new metric that we talk about today. And the next one we talk about is the recall or sensitivity, right? They are the same thing, just different names. So the definition of recall is the proportion of the true positives to all actual positives, right? Actual positive means the first column. So that's the true positive divided by the sum of the first columns, the first column. All right, so what it really means is I want to see if I catch all of the positive cases, right? So that's actually determined by, the value is actually determined by false positives. Yeah, this is actually a typo that I should detect it earlier, right? This is Fn, right? It's true positive divided by true positive plus false negatives. So it's actually decided by false negatives, right? That means if false negative is greater than 0, that means there are some cases which are actually positive, but your model predicts them to be negative. That means you didn't catch those positive cases. If recall is 100%, that means false negative is equal to 0. that means you catched all of the positive cases. If recall is low, that means there are many cases you didn't catch. That means you have a lot of false negatives. All right, so you can see a clear contrast between precision and recall. Precision is about, let's look at those predicted positive cases. How many of the predicted positive cases are actually positive? That's precision. And recall is, let's look at the positive cases you predicted. And let's see if your predicted positive cases cover all of the actual positive cases. Are there any cases that are positive, but your model didn't catch it? So this is about recall. So use this example again. We have 100 people and 5 people have cancer, and model is bad and predicts every case as cancer. In this case, what's the recall, right? First, true positive. And what's true positive? That's 5, because your model predicts every case as cancer. There are 5 people who have cancer. Those 5 people, they're true positive. And what's the true positive plus false negative? Right? That means true positive plus false negative. That's the first column. That's the actual positives. Right? Actual positives is 5. So it's 5 over 5. That's 100%. Right? In this example, the recall is 100%. But what is precision? Precision is only 5%. Right? So now you must wonder, the recall gives us a very good one, 100%, that's pretty high. And the precision gives us a really low score, which is 5%. How we can treat precision and recall. All right, so we'll look at the next topic, which is the precision versus recall. All right, so how to interpret precision and recall, it's also based on different cases. All right, so for example, we can also use the cancer detection problem and spam detection problem as 2 examples here. So for example, you have a model for the cancer detection. Then you want the model to have, you want to minimize the false negative, right? Because false negative is very dangerous, right? Your model detects, your model labels a person as no cancer, but actually the person has cancer. So you want to minimize Fn. So when you minimize Fn, you are actually trying to increase recall, because Fn is decreased, the recall is increased. So in this case, for the cancer detection problem, you actually prefer a model which has a higher recall. For the spam detection, right, you want to have fewer false positive case. Right? For the fewer false positive case, that means you have a higher precision. False positive here means it predicts a important email or regular email as spam. You don't want that case to happen. So you want to decrease FP and increase precision. So in this case, you may want a model that has a higher precision. But what we should pay attention to is in the process of recall, increase or maximizing recall, we still need to take care of, for example, for the cancer detection problem, we want a model that has recall as large as possible, but we still need to pay attention to the precision, right? Actually, recall and precision, right, they move in opposite direction, right? If you increase precision, it reduces recall, and if you increase recall, it reduces precision. Right, so when you are trying to find a model that has a higher recall, but you still need to pay attention to precision. It can't be too low, right? So for example, we just had an example here. This is really bad model, predict every case as cancer. So the recall is really high, it's 100%. But can you use it only because you want to reduce false negative? No, because the precision is really low. It's just 5%. Right? So you still need to, when you are trying to get a model with a high recall, you still need to have relatively high precision. It cannot be, for example, as 5%. Right? Same thing for the other case. When you want to increase you want to increase precision, you still need to make sure the recall is not significantly low. Right, so the first part about precision and recall, and the second part is about the trade-off between precision and recall. Right? As we mentioned, one increases, the other one will be reduced. Right, so, and why is this true? Right? Why precision and recall, there's a trade-off between them. Right, so we use this example here. Right, this is for the digits detection or identification. So, and you can see the model here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 cases. We have 12 images. Right, each image contains a number. And suppose we use, for example, we use the softmax regression, or let's say we just look at a binary classifier. Let's say we just use logistic regression, right, to detect the 5 and non-5. And we have a score. The score is simply beta transpose x, right? Beta transpose x, if we set the decision boundary to be beta transpose x equal to 0. If it's greater than 0, then we classify the number as 5. If beta transpose x is less than 0, we classify it as non-5. But we can look at different thresholds. Right? Suppose this thresholds corresponding to, right, suppose this points corresponding to beta transpose x equal to 0. That's the regular threshold we use. But actually, we can increase the thresholds. Because if you use beta transpose x equal to 0, there may be more cases that you will get it wrong, right? Which means it's not a 5, but you predict it to be a 5. Right? So it's a false positive. Right? It can happen. So we can actually increase the thresholds, right? Let's look at this point here. Maybe it corresponds to beta transpose x equal to, let's say, 1000. Right? If you think about the decision boundary here, let's say these are crosses, these are circles. Circles, crosses. Our decision boundary, right, is here. Right, that corresponds to beta transpose x equal to 0. So around this boundary, you will see a lot of misclassified cases. Right? But how can you make sure you have more precision? That means you predicted the cases as positive and they're truly positive. Right? You can actually move this line to here, for example. Okay, there are more crosses here. And you can see the precision is actually increased because all of the cases are crosses, right? They're positive case. This is a negative case. We predict these 3 cases as positive, but they're truly positive. But if your the threshold is here, corresponding to beta transpose x equal to 0, then your precision is not 100% because this case is predicted as positive, but it's actually not positive. So you have a false positive case in this case. So your precision is less than 100%. So when you increase the thresholds, that means when you move this decision boundary to the right, you actually increase precision. when you actually move this line to this way here, you can see your precision gets worse. Because if your decision boundary is here, then this case and this case and this case will all be classified as positive, but they are false positives. So you have a lot more false positive cases, then your precision will be decreased. Right, but when you move the line from here to here, actually the recall will be better. Right? Let's see, we have a positive case here. So this is square, right? This is square. And why is this true? When we move the decision boundary from here to here, that means we decrease our threshold. Right? That means from 0 to maybe negative 100. Right? And why the recall will be increased? If the line is here, let's look at the recall. Right? Recall means, did you catch all of the positive case? We didn't catch this case. If the line is here, this case is actually positive, but it's predicted as negative. So we didn't catch this case. So in this case, recall is less than 100%. But if the line is here, then this case will be predicted as positive. Positive, all of the crosses will be predicted as positive. So we catch all of the positive cases. So recall will be 100%. So recall will increase. So this is one way to illustrate the conclusion that increasing precision reduces recall and vice versa. Another way to do it is we can do it quantitatively using this example here. Suppose our initial threshold is here, but that means after, to the right of this threshold, we'll predict it as 5, and to the left, we'll predict it as non-5. All right, so using these thresholds, let's look at the precision of our model. So for these 5 cases, 1, 2, 3, 4, 5, all of the cases will be predicted as 5. And this one is a false positive. So for the 5 cases where we predicted as 5, so the denominator will be 5 for precision. How many are predicted correctly? 1, 2, 3, 4, only 4. So it's 4 over 5. That's why we have a 4 over 5 here as the precision. If we move our thresholds to here, what's the precision? It's a 3 over 3. We have 3 cases where the model predicts the cases to be 5, and all of the predicted cases are correct. So it's 3 over 3, so that's 100%. So you can see the increase of the precision. And if you move the precision here, actually reduce the threshold, and the precision actually gets pretty bad, because 1, 2, 3, 4, 5, 6, 7, 8, you predicted 8 cases to be 5, but only 1, 2, 3, 4, 5, 6 of the 8 cases are correctly predicted. So it's 6 over 8. Let's look at the recall. If the threshold is here, so we want to look at what's the percentage of positive cases that we caught. So if the threshold is here, we caught 1, 2, 3, 5. So we'll catch 1, 2, 3, 5 positive cases. But how many positive cases are there altogether? 1, 2, 3, 4, 5, 6. There are 6 positive cases, but we only catch 4 of them, right? So it's 4 over 6. And we increase the threshold, then the precision increases, but the recall actually decreased, because we only caught 3 of the 6 cases. So that's 50%. That's a drop from 67%. We put the thresholds here, we caught all of them. So the recall is 100%. So thresholds, decreasing thresholds, you can increase recall, but you will decrease precision. When you increase thresholds, then you increase precision but decrease recall. So you can see the trade-off between precision and recall. Right? Again, thresholds plays a very important role. It's very important concepts of our discussion in this lecture note. Right? The thresholds basically means, right, for example, the beta transpose X case, right, for logistic regression, right? If it's greater than 0, the 0 is the threshold. You will predict it 1. Right? If it's less than 0, you will predict it as 0. You can also set this as, for example, use 1,000. Right? That's an increase the threshold. Right? So if, for example, in this case, if we use 1,000 as the threshold, then if beta transpose X is greater than 1,000, then we predict it as 1. If it's less than 1,000, we predict it as 0. So that's what the thresholds mean. In this case, you increase from 0 to 100, you actually increase precision. Right? There's a great chance that when you predict 1, you predict it correctly. Right? But in this case, you will miss a lot of positive cases. Right? Like this, you increase threshold, you missed these 3 correct cases. All right, so this is an illustration about the trade-off between the precision and the recall. So actually, we can jump over 1.1.5 specificity, and we can directly look at F1 score here, right? So we just mentioned sometimes we want to have a higher recall, and with some sacrifice of precision, right? Sometimes we want higher precision at the cost of recall. So can we combine? But when we increase recall, we don't want the precision to be too small, right? And also when we prefer a higher precision, we don't want the recall to be too low. So here comes the problem, right? Can we combine both precision and recall, right? To have a synthetic or a single score that represents both of recall and precision, right? So this is the F1 score. So it's a single score that represents both. So you can think about an easier way to do this. Let's simply do an arithmetic mean, which means just the mean of precision and recall, and we use it as the score or the unique score or the single score that represents both. Does it work? Actually, a lot of cases it doesn't work because so we use the example here, right? We want to predict frauds, for example, application of credit card, right? Some can be frauds and some can be not fraud, right? If it's a fraud, then it's positive. If it's not fraud, it's negative. Right? In this case, it's true positive 3, true positive 3. This is a false positive, it's 97. It's predicted as fraud, but it's actually not fraud, so it's false positive. In this case, we can compute the precision 3 over the sum of first row, so that's 3%. Recall is 3 over the sum of the first column, that's 100%. If and also you can see this is actually a pretty bad example here. Sorry, I should say a pretty bad model here, right? Because it predicts a really large portion of the case wrongly, right? Because it's they are actually not fraud, but it predicts them to be fraud. So this is a pretty bad model. But if we just use the arithmetic mean, we get 100 plus 3 divided by 2, that's about 51%, so 51, 52%. It's not really that bad. The 51%, but it doesn't connect 51% to a model as bad as this. So it's not a good way to do an arithmetic mean. And there's a better way to do this, right? This is called the harmonic mean. The definition of harmonic mean is 2xy divided by x plus y, right? in contrast to the arithmetic mean, which is x plus y over 2. And what's the advantage of using this? The advantage or the property of harmonic mean is if x and y, they're pretty close, then 2xy over x plus y, they are, the value is about x or y if x and y are close, right? The extreme case is x and y are equal, then you have 2x squared divided by 2x, you get x. So if x and y are equal or close, the average will be the value that's close to x or y. If one is really small, then this number will get closer to that smaller one. Right? For example, if x is 3%, y is 100%, that finds the harmonic mean. The harmonic mean is actually 2 times 100%, that's 1. 3%, that's 0.03, divided by 1 plus 0.03, that's 1.03. So it's about 6%. That gets closer to the smaller one, right? So this is a good way to do the average, because if you have a model like this, the precision is really, really small, right? We don't want this case, right? We talk about when we want to increase recall, but we don't want precision to be too low. In this case, actually, this average, the harmonic mean actually indicates it's a bad case because it moves closer to the smaller value. And that's actually the definition of the F1 score, which is a combination of both precision and recall. Right? So F1 score is defined as 2 times the harmonic mean of precision and recall. So it's 2 times precision times recall divided by the sum of precision and recall. And it can be proved as true positive over true positive plus false negative plus false positive divided by 2. Right? So you prove this as a homework example later. Right? So F1 score makes sense. Right? For example, if both are 60%, 60%, this will give the F1 score will give you 60%. If one is really bad, it would give you a bad score. If both are high, it will give you a high score. Right? So this makes sense. F1 score makes much more sense compared to the arithmetic mean. And we use the harmonic mean for precision and recall. We define F1. F1 is a score that combines both precision and recall. All right, now let's go back to specificity here. So specificity is the definition of specificity is true negative divided by false positive and true negative. So it's similar to recall here. Recall is true positive divided by sum of the first column. And specificity is the opposite, right? That's the true negative divided by the sum of the second column, right? So that's similar to the interpretation of recall. For recall, we want to see what's the proportion of the positive cases that we actually catch. By our model. So the specificity is the same. That's the proportion of the negative cases that our model actually caught. Right? So we can interpret it in a similar way. So look at the example again here. 100 people, 5 people have cancer. The model is bad and predicts every case as cancer. So our denominator here, denominator means the actual negative case. The actual negative case is 95 because 95 people actually have no cancer. So the denominator in this case is 95. And what is true negative? True negative is 0 because the model predicts no cases as negative. So true negative, both true negative and false negative, right? They're 0. So it's 0 over 95. In this case, you get 0%. Right, so we'll not use specificity directly, but actually later you will see we use it for the ROC curve. but we use 1 minus specificity. Okay. All right, so now we move on to the ROC curve and area under curve, right? It's AUC. So this is a very important measure. First, it's a graphical visualization, and AUC serves as a single number. It serves as a metric or measure for your classifier. It's also a very frequently used measure to compare models. So we'll spend quite a long time, right, in this lecture to talk about what is ROC curve and how to interpret the ROC curve. All right, so let's first take a look at the ROC curve, and then we'll introduce what AUC is. Right, AUC is pretty. Once we know what ROC curve is, then we can understand AUC pretty easily. So first, the ROC curve is actually a plot of TPR, which is true positive rates. Right? True positive rate is actually recall. Right? That's the positive, true positive cases divided by all of the extra positive cases. So that's true positive rates. Right? That's recall against the false positive rate. The false positive rate is actually the false positive cases divided by the actual negatives. And also it's equal to 1 minus specificity. Right? You can think about it as true positive. You can think about it as recall versus 1 minus specificity. And you might wonder, why do we have, right, for each point on the curve, it's 1 specificity, it's 1 recall, right? Why do we have so many recall, right? This is because we are looking at different thresholds, right? Let's go back to this example here. 1 threshold, you have a recall, and you will have a specificity, then you have 1 minus specificity, then you have the false positive rate, right? So for another threshold, you have a recall, which is true positive rates. You will also have false positive rates, right? Not precision, but false positive rates. So based on different thresholds, you have different points, right? Different numbers for this, different numbers for this recall, and similarly for false positive rates. So that's why we can plot this curve. Right? Each point corresponds to a certain threshold. And to understand this, the curve, and that means how to understand this curve is maybe a little bit more complex, but how to use this curve to compare a model, that's pretty easy, right? So the first thing, once you have this plot, right, how can you compare the model, right? First, if you can plot for 2 models, you plot this ROC curve. So one, for example, is like this. The other one is like this. And this means this one is better. Right, so it's, let's call this 1, let's call this 2, right? The model 1, the ROC curve of model 1 is more to the top left corner compared to the ROC curve of model 2. That means model 1 performs better than model 2, and later we'll explain why. And you can also see there's a straight line here, plots here. What it means is this is the totally random model, which means the model has no predictability, simply randomly say or predicts a certain case is 0 or 1. So it's a purely random classifier. And the curve here, or the straight line here, is for the random classifier. Right? This is a pretty bad model, right? It doesn't have any predictability. It's simply just randomly assign a label 0 or 1, right, to a case. But this is how to use it. Right? If it's more to the top left corner of the curve, then the model is better. And equivalently, you can use the AUC, which is a number, right? The AUC for ROC, that's the area under this ROC curve. The best you can get for AUC is 1. That means the best case for ROC is actually this. Right? This is 1, a straight line. This is the best case for ROC. So in this case, this is a 0, this is 1. So the area under the best case, that's 1. That's the best possible you can get for AUC. Right? But for worse than ideal case or just a or normal case, ROC will look like this. So the area under this ROC curve, which is AUC, area under the curve, that's smaller than 1. So if you're comparing these two models, definitely the AUC for model 1, that's better, that's larger than AUC for model 2, because the area under the first curve is larger than the area under the second curve. Right? So equivalently, you can use AUC to compare the model. So now we would like to dig into the mechanism of ROC. Why do we plot TPR versus FPR? And we will use this to compare models, right? For example, why is it valid that if the ROC curve is more close to the top left corner, then it's better, right? So we'll dig into the different cases here. All right, so all right, so before we actually talk about the mechanism of ROC, so we will try to understand what this means here in this paragraph here. So the one thing is about how to interpret AUC, right? AUC, the higher the better. The closer to 1, the better the model is, right? That's something we have talked about. And you can look at the random classifier here and what's the AUC, right? Because it's a straight line y equal to x. So the AUC, that means the area under this straight line, right? 0, 1, right? This is 1, that's just a 1/2, 0.5. So if your AUC is 0.5, that means your model is actually the random classifier, right? So at least you should have a model which is above, whose ROC curve is above this straight line. So that, for example, this is not a good model, but actually this is better than the pure random classifier. And another thing we want to talk about is about the trade-off of TPR and FPR. So what this really means is when you want to increase TPR, so want to go this way, then you have to move this way. So what it means is if you want to increase your TPR, you need to go this way. That means you have to increase your FPR. That means if you want to improve your recall, then you have to increase the false positive rate. So in the cancer detection problem, that means if you want to increase your recall, that means you want to catch many positive cases as possible, then you will increase the false positive rate. That means you will inevitably classify some non-cancer people as cancerous. Right? So you want to increase the recall, then you have to increase the false positive rates. Right? And actually, this curve also tells us something when we're choosing the model. So suppose we're doing the cancer detection problem, so we want to increase TPR, right? Then which is the point that we should use? That means a point actually determines the threshold. That means what threshold we should use. So actually, you can see there's a sharp increase of recall. So actually, at this point here, let's say around this point, right, the curve becomes more flat. Right? That means we may just stop here, because when we are moving to this point, we are at the cost of increasing the false positive rate a lot. Right? But from here to here, it's worth it, because we only increase the positive rate from 0 to this point here, and maybe this 0.4, but actually we increase the recall from 0 to about 0.8, so that's worth it. After this point, I think the trade-off is, or the cost is too big. So maybe I will just look at the threshold at this point. I will use that threshold for my model. Right, so this is also, the ROC curve also gives us a way to choose the model. Right, so more extreme case you will see is like this. Your ROC curve, right, that's like this. So you want to use this threshold here? No, you want to use this threshold here. Right, it's almost close to 1 for the recall, but the false positive rate is still small. But at this point, you didn't increase your recall. Maybe you only increase your recall by a little, 0.001, but you actually increased your false positive rate a lot. So to choose the threshold, you will use the threshold corresponding to this point. And that's it. That's the optimal threshold, or the threshold that actually makes sense. Right, so this is another implication of the ROC curve. So now we'll actually interpret the ROC curve, or talk about the mechanism of ROC curve. All right, so we'll use these 4 plots. 1, 2, 3, 4. We'll use these 4 plots to illustrate the ROC curve. So first introduce what the green line means and what the red line means. So the green line you can think about as the histogram of actual negative cases. Right, histogram, what it means, for example, corresponding to threshold points, this is 0 to 1, this is 0.5, so this is about 0.25. Right, it corresponds to maybe 1,000 cases. Right, corresponding to this point here, maybe 0.1, there are maybe 500 cases. Right, same thing for true positive case. Right, corresponding to 0.75, there are 1,000 cases. And similar. So you can think about it as the histogram of actual negative cases and actual positive cases. And if we normalize it, so this can be viewed as the density of the true negative cases. Right? This can be viewed as the density for the true positive cases, or distribution of negative cases and positive cases. And here we can think about the area. The area of the two curves is the total number of, the area of the green curve is the total number of actual negative cases. The area of the red curve is the total number of actual positive cases, right? Because the definition of the curve is histogram. So you can think about the area. Right? They are the total number of cases for each label. All right, so first, let's understand these two curves, all right? So then you may wonder why we have exactly the same curve here, right? It's like the same distribution or same histogram, right? Just for easiness to illustrate. So we just assume these two curves are the same, right? But in real problems, they're different, but it doesn't affect our analysis, right? So we just use the same histogram or the same distribution. So the first model is the best model, that means our model, you can see there's no overlap between the two cases. This is the threshold. After the threshold, it predicts positive. Before the threshold, it predicts negative. Right? So you can see the two cases, positive case and negative cases, they're separated. So this model has good ability to separate the two cases. This corresponds to the most ideal case. And when we draw the ROC curve, look at the red line here. That's the ROC curve. And the area under the ROC curve, that's equal to 1. And I'll explain why, if this is our model, which separates the two cases clearly, why this is the ROC curve. So we can look at the thresholds, for example, let's say we look at the threshold here. Let's say the threshold is here, it's 0. If our threshold is 0, let's find the recall, right? The y-axis is recall. Remember the x-axis is 1 minus, right, specificity or false positive rates. Right, specificity is the proportion of the negative cases that are captured. So if the threshold is here, what is the recall? That means the proportion of the positive cases that are captured. If threshold is here, to the right of the threshold, they will all predicted as positive cases. So we actually captured all of the positive cases here. So it will be 1. TPR will be 1. Right? TPR will be 1. Now let's look at the false positive rates. Right? False positive rates. So let's look at a false positive rate here. And FP here, let's just make an assumption. There are 100 cases that are negative. There are 100 cases that are positive. So the area for this green curve is 100. The area under the red curve is 100. Right, so now let's look at the false positive rates. Right, false positive rates, remember that we can use 1 minus specificity, right? That depends on you. So let's use false positive rates plus true negative rates. In this case, false positive, how many cases are there? 100. They are predicted as positive, but they are actually negative. So that's 100. That's 100 plus nothing is predicted as negative, so it's 0. So the false positive rate in this case, that's equal to 1. So what's our point corresponds to the threshold? That's 1, 1. That's this point here. Corresponding to the thresholds, now we can make a plots on this ROC curve. That's the plot here. Now we gradually increase our threshold. Now suppose our threshold is here. To the right of the threshold, everything will be predicted as positive. To the left, everything will be predicted as negative. Now let's look at the recall. The recall is still 100% because we captured all of the positive cases. So it still be 1. Recall still be 1, but the false positive rates will change. In this case, the false positive rates is equal to false positive. What's the false positive? False positive cases will be the area of this vertical line, the threshold, and this green curve, part of the green curve. If the total number of cases is 100, then this case may be 85. Right? The area is maybe 85, so we'll just use 85. So we use this as false positive because we predict those 85 cases as positive, but they are not positive. So it's 85 over 85 plus, we actually don't need to add the denominator, because denominator is just actual negative. Actual negative is always 100. So it's 85%. Now we have another point corresponding to this threshold. Our true positive, our recall is 1. Our FPR is 0.85. So 0.85 is about here. So we have a point here. Or you can see if the threshold is here and the point is here. Right? Let's gradually move our thresholds to here. Now our threshold is here. So what's the recall? Recall is still 100% because it captured all of the positive cases. And what's the false positive rates? It's 0 because there's no negative cases that the model predicts as positive. Right? Because for all of these negative cases, they're predicted as negative because it's to the left of this line. So in this case, false positive rate will be 0. So now we have another point, 1, 0, or 0, 1. That's the point here, corresponding to this threshold. Right? So as you move your threshold from 0 to 0.5, you actually get this part, the vertical line here. Then we move it further. Let's see, the threshold is here. Then now your recall is no longer 100% because you missed this many cases, right? This is about 15 cases. This is about 85. The area is about 85. The area here is about 15. So you missed the 15. You captured only 85. 85 out of 100. So your recall here is 85% or 0.85. Right? Let's write it here, 0.85. That's for recall. And what's the false positive rates? There's no false positive case. All the negative cases are classified as negative. So it's still 0. So now we have a point, 0.85, that's here. Then we move it all the way, so this point, the point will go down. Then when we hit the thresholds, when the threshold hits 1, the recall will become 0 because we missed all of the positive cases. So that will be 0. Recall is 0, and the false positive rate is still 0 because we classified correctly all of the negative cases. So it's 0. So that's the point here. So when you move the threshold from here to here, we actually recovered this vertical line here. And we get our ROC curve. And that's the best case because the classifier can clearly separate negative case and positive case. In this case, the best, the ideal ROC curve is in this form. And what's the AUC here? That's equal to 1. Right? The AUC equal to 1 actually means it can predict 100% of the cases. So this is ideal case. Right? In the less ideal case, let's say your model cannot clearly separate the two cases. So there's an overlap. Right? So in this case, you can think about, let's move back to the crosses and squares. Right, this is too ideal. Undo. Okay, so this is right. So let's do this. All right. So corresponding to the first case. So this is your data. Right. This is a positive case 1. This is a negative case 0. So for the first model, it can be like this. So use a red one. So if your model is like this, so it clearly separates the positive case and negative case. Right? This clearly separates positive case and negative case. That will be something like this. And the second model is similar or analogous to a model like this. Or maybe let's do this. Probably this is better. Right, so there's some overlap. Right, to the right of the threshold, you will see some negative case. They're not all positive case. To the left of the threshold, you will see there's some positive case. Not all of them are negative. So this corresponding to this case. There's an overlap between true negative and true positive. That means your model can detect or can separate most of the positive negative cases. But there are some that it cannot separate. So in this case, let's go through this process again. Suppose the threshold is here. What's the recall? The recall is 100% because it captures all of the positive cases. And what is the false positive rate? The false positive rate is 1, right? Because all of the negative cases are actually predicted as positive. So they are the false positive rate is 100 over 100. That's 1. So we get 1 points. That's the point here. Then we move the threshold to here. Still recall is 1. And now the false positive rate is about 85. That's the area for the square under the screen curve. And this vertical line, that's about 85 divided by 100. So 0.851. Right. So 1 point is actually here. Let's move the threshold to here. When we move the threshold to here, the recall is no longer 1. The recall is less than 1. So it's about 90 and versus 10 or 95 versus 5. Right? Let's say 95 versus 5. So about 95%. So recall is 95%, and the threshold. And what's the false positive? False positive, that the cases will be the area under a green curve and this vertical line. It's about 15 versus 85. So it's 15 over 100. That's 0.15. So we have a 0.15, and we use 0.95, right? So that would be this point here, or this point here. And we'll further move the threshold. Let's move the threshold here. After we move the threshold here, so we correctly captured about half of the positive cases. So our recall is about 0.5, but our false positive rate is 0. So we have a 0.5, a 0.5. It's not, the graph actually does not exactly match, right? But we know what this actually means. Let's say this is 0.5. So we get a point here. And then we move our threshold here, so we get a 0 recall and 0 false positive rate, so get these points. So you can see when we move the threshold from left to right, we move the point all the way from here to here. But it's no longer a straight line, horizontal line, and then horizontal line and the vertical line. Right? That's because we have overlap here. So the AUC in this case is no longer 1, it's 0.7. Right? That's caused by the overlap. Right? This means 70% chance that the model will be able to distinguish between positive class and negative class. Right? If, for example, if our threshold is here, right, you cannot. So these cases will be predicted as positive, but they are actually not positive. So, right, these cases will not be correctly distinguished. So this is the second case, but it's not too bad. The overlap is not that large. That's further increase the overlap. Right? The extreme case is the two density or two distributions or two histogram, they totally overlap. And let's see what will happen. First, we do the same thing. Threshold is here. We captured all of the positive cases, so recall is 1. And we also falsely predict all of the negative cases. So the FPR, the false positive rates, is also equal to 1. So we get this point here. All of these 100 cases for the green curve, we actually predict them to be positive. So it's false positive. That's 100 cases over 100 actual negative cases. So it's 100 over 100, that's 1. So it's 1, 1. This threshold gives us this point. Let's move it to here. The threshold is about 0.35, something like that. And let's look at the recall. The recall, since we can't capture all of the positive cases, but it's about 20%, 80%. Right? So the recall is about 80%, 0.8. And what's the false positive cases? The false positive cases is also 80. That's the green curve plus the vertical. If we use 80 for the cases we capture, the positive cases we capture, and the it's also 80 for the falsely predicted the FPR case, right? The false positive case. It's also 80, since the two curves are the same. So it's 80 over 100. So that's also 80%. So it's 80, 80 in this case. And we move it all the way to the middle. The middle will give us 0.5, 0.5. Move it all the way to here. This will give us 0, 0. So move your threshold from here to here. You get this line in this direction. All right, so we have gone over 3 cases. Right, so this is the case where you have a random classifier, right? This is and you got the ROC curve. And you may think this is the worst case, but actually there are more. There are worst case that's worse than this. And the case is actually we predict the you have a model that predicts true positive to be negative, right? Predicts true negative to be what I should say is you predict positive case to be negative, predict negative case to be positive. Right? So this model is just it's actually reciprocating the classes. Right? So in this case, let's go through this process again. So the threshold is here. You actually captured all of the cases. So your recall is 1, but you actually predict all of negative cases to be positive. So the false positive rate is also 1. So you have this point here. Then you move to here, threshold. Then your recall is no longer 1. You only captured half of the positive cases, so that's 0.5. Recall is 0.5. Again, FPR is 1. So you get the point here. Then you move to here. Again, your recall is actually 0 because you captured none of the positive cases. And also FPR is still 1. So you get this point here. For this threshold here, recall is 0. And here, the false positive rates is half. And that's 50%. 50 divided by 100, that's about 0.5. That's the point here. And go to here, recall is 0, false positive rate is 0. So when we move the threshold from here to here, we actually get this curve. that's the worst case actually we can ever get, right? So you can see for ROC curve, good models will move this way, get better, get better, get better, get better. A bad model will move this way, right? Go this way, get worse, get worse. What's the worst case? Right? It's like that, right? So actually, we have gone through all of the cases and we have shown why ROC can be used that way. Right? More to the top left corner, the better. Where the AUC is larger, the better. Right? So hopefully. After I've gone through all of these cases, you have better understanding of ROC. All right, so we move on to the example here. So we use a data set which is built in scikit-learn. So it's called MNIST data sets. So it contains 70,000 small images. Each image contains a number. It's handwritten, and they're stored as each image is stored as a so 28 by 28 matrix, right? It's not stored as a matrix, but it's stored as a vector, right? The vector is 784 entries, right? So each image is represented by a 784 vector. Actually, what it means is actually a 28 by 28 matrix. So if you look at the 28 by 28 matrix, each cell of the matrix actually represents or each number of the matrix, or each entry of the matrix represents an intensity. So the pixels intensity is from 0, that's totally white, right, or 250, that's black. So you can see here, this is a black, this is white. Right? There's no handwriting here, so that's 0. So this is how the image is represented by numbers. So we'll take a look at the MNIST. So later we'll also use this data set to test the other algorithms. This is like, as I mentioned here, it's like the hello world of machine learning. When you're learning a new programming language, you always want to see how to print out something like hello world. So that's the first line of code you will ever learn for that programming language. Same thing here when we're learning a new, or when we're developing a new classifier, we want to apply it to MNIST datasets. Right, so to get the dataset, we use the sklearn.datasets.fetch-openml. Right, so what it actually does, it actually get the data. So it's get the data from OpenML. So this is a website for machine learning. So try to fetch the data from OpenML. So we specify the name of the data and the version. Right? We just use the first version. So the code will find the data there and get the data to the memory. So now MNIST, as other data sets, as you see from the iris flowers, you can see it's a dictionary, and we look at the keys of dictionary. So here, data is the feature, right? Targets is just the labels, and also it has the feature names and description and other things. So we only need the data and targets here. So we get the feature matrix. It's a dictionary. This is how you get access to the data. The data is the key, right? Target is another key, right? Access the data and access the targets. So we look at the size of the matrix. The matrix is 70,000, so we have 70,000 instances, and the feature size is 784 because we know each image is represented by 28 by 28 matrix. Each entry of the matrix is the pixels intensity, right? So we have many columns, and we have also 70,000 labels. And printouts, we can also print out labels. For example, we look at Y0, the first label. right? So it's equal to 5. And we can see there's a pair of quotation marks. That means they store the label as strings. So that's why we want to remove the quotation mark. That means we want to convert the string to numbers. So that's what we're doing here, y equal to y dot s type. Right? So this is explicitly convert the type to, so this is uint. Int means integer, 8 means 8 bytes. Right? Integer represented by 8 bytes, and u means unsigned. Right? It doesn't use a negative number, negative 8, right? Or negative 2, right? Just unsigned integers with 8 bytes. All right, so yeah, we're jumping over here, right? So we can do some visualization here. Let's take the first instance of the data. All right, so for the code, please read the comments. I wrote these comments to help you understand the code better. So x0, that's the first row, all of the columns. So we just extract the first rows. And then we do a reshape because the 784 really means 28 by 28 matrix. So we do a reshape to make it from 1D vector to a 2D NumPy array or 2D matrix. So now digits image now becomes a 2D array. It's 28 by 28 2D array. Then you can call the image show, so im show, and give the 2D array as an input. So it will print it out. Here you can also set the color map. Here we only use the binary color map just to show black and white, right? And black, white, gray as the color map. If you want to show some more colorful ones, where you can, there's a bunch of built-in color map that you can see from, or you can use from matplotlib.cm. Here, MPL, what I'm doing here is just import matplotlib and give it an alias, just MPL. So MPL is simply matplotlib. All right, so we see this is a number 5, right? And also we look at its label, it's also 5. Right? So for each image, it has a label. So it's the data is just there, right? Just we need to use a classification problem and test whether the classifier works better than some commonly used method, or our newly developed method works better than the existing method. So we can use this to test our method. All right, so here we want to use this data set to illustrate all the metrics we just talked about, how to use Python to get all of the metrics. All right, so we change the label to integer. Then we want to have a training set and test set. So actually, the NIST dataset has already been split into a training set. The first 60,000, that's the training set. So we just extract the first 60,000 rows of X, and that's the training set. After the first 60,000 images, that will be used as test. Same thing for training. For training data, the first 60,000 numbers of Y will be used as training data, and the next 60,000 will be used as test data. All right, then we'll build a 5 detector, 5 versus non-5. Right, we will just do a simple binary classifier. So we need to get the correct label, because now our label is not just 1 and 0. It has 1, has 0, has 2, have 9. And what we need to do is something we did before. So we compare our label with 5. If it's equal to 5, it's 1. If it's not equal to 5, it's 0. So we get a new label. That's a new target. That's a Y trim, call it Y trim 5. So this is just 1 and 0. But actually, it's actually true and false. You can also set them to integers. Right here, we'll just use it. The true and false works well. So you can think about this 1 train 5, just the target vector of 1 and 0. Right? Same thing, we do the same thing for the tests, test target values. Right? Just 1 and 0. There's no 5, no 6, and no other values. Simply a binary problem right now. So we use logistic regression, and we use the SGD gradient, the stochastic gradient descent, because we have 60,000 training instances. If you use the logistic regression, it can take a long time, right? So we just use stochastic gradient descent. So we use SGD classifier. Remember, we need to set the loss function to be log. So now it implements logistic regression, right? To make it everything reproducible. Right? In the previous class, we talked about using random states. So set the random state to be 42. You can use any other number, right? So once we set the random states, then every time we run it, there's no randomness. And we do a fit, so we train a model, use the training data and the training labels, and then we make some predicts. For example, digits is the first instance. We predict for the first instance to give us a true, which means it says it's a 5. Right now, we can look at how to get different performance metrics. For example, to find accuracy, we just do first we make a prediction for all those test cases. So these are predicted labels. And then you can simply call accuracy score, which is imported here from the sklearn.metrics. You can import accuracy score. And we have already done that from the previous lecture. Okay, and then we can see the accuracy score. Printed out, it's 97.04, right? So the accuracy score is not bad. And then we look at the confusion matrix. Confusion matrix can also be imported from sklearn.metrics. Then use the true label for the test data and the predicted label for the test data. You get this confusion matrix. Over here, I want to emphasize this is the confusion matrix is differently defined compared to what we talked about before, right? So here, the ij term, that means this is the 0, 0 position. This is 0, 1. Right? This is a 0, 1, 0. This is 1, 1. So the ij means, ij subscripts means the first number means the actual, right? This is the actual class. And the second one means the predicted class. All right, so in this case, that means look at the columns here, it's about predicted. And the columns are about prediction, but the rows are about actual cases. And also the first one, remember in our confusion matrix, we use positive, but now it's negative. So it's totally different. The confusion matrix is totally different. Right, so it's actually Tn, Fp, Fn, Tp instead of Tp, Fp, Fn, Tn. Right, so this is something you need to pay attention to. So here, suppose we want to get so this is the confusion matrix we get. And actually based on the confusion matrix, we can compute precision and recall. Right, for example, what is precision? The precision is simply Tp divided by Tp plus, so Tp plus Fp, right? So it's 682 divided by 682 plus 86. Right, that's given here, that's 0.888. Right, instead of doing this, we can simply call the precision score function imported from sklearn.metrics. Right, again, use the predicted label and the true label, you get the same thing. Again, from the confusion matrix, you can compute recall, or you can use the built-in function record score imported from sklearn.metrics. Give you 0.76. It's the same as it's a true positive divided by true positive plus false negative. Right, so it's 682 divided by 682 plus 220. Let's give you the same number. Right, so you can use precision score, you can use recall score, you can use accuracy score, you can use confusion matrix to get these things. And what about F1 score? You can also get F1 score by just to call F1 score. It's also imported from the same package to get about 0.82. Right, this makes sense because the precision here is 0.88%, and the recall is 76.5. A combination of both using the harmonic mean, it gives a 82%. So it's not bad one, right? But not great either, right? Look at the precision, look at the recall, look at F1 score. It's not the best model that you can use, but it kind of works. All right, so we can also get the decision function, which is actually the score. If we want to look at the score, right, this is how you get the score. For example, for the first instance, you can get the score. Again, what is the score in this case? That's beta transpose x, x1. That's in this case the first instance. Right, that's the linear regression part. Remember, if it's zero, it's greater. It's zero. That's the decision boundary. If it's greater than zero, then it's classified as positive. If it's less than zero, it's classified as negative. It's pretty much further. It's pretty much far away from zero. Right? So that's just look at the score here. That's a pretty safe case to be classified as 5. Right? To get the score, we can call the decision function. Right? Then we check whether it's really beta transpose times x. We can do this. Right? This is the beta 0 plus beta 1 times x1 plus beta 2 times x2 and so on. You get the same number. So the decision function actually gives us the score, which is beta transpose times x. All right, so how to plot the ROC curve? Right? This is how we can do it. We first get all the scores of the test cases. All the scores. So we call it test score, y-test scores. After you get the scores, then you just call this ROC curve, which is also imported from the same package. And what you need to, what the inputs are first the y-test 5, that's your labels, right? The true labels and all the test scores. That means all of the beta transpose times x, all of these numbers, all of these scores. So you need the true labels, you need the scores. Throw them in this ROC curve, it will give you 3 things. Right? That's what you need. You need FPR, that's false positive rate, that's the x-axis. The true positive rate, that's the recall, that's the y-axis. So based on TPR and FPR, we can make the plot. So we do a plot FPR versus TPR. So sorry, it's TPR versus FPR. We set the line width to be 2, and we make this y equal to x plots. That's just 0, 1, 0, 1 to give you this y equal to x plots. Our x label false positive rate and true positive rate. So you get this ROC curve. It looks nice. It's very close to the exact case. That's this. But it's not. It's still not there yet. But it's not bad. And also we can look at the AUC number. That's the area under the curve. So we can call ROC AUC score. That's also imported from the same package. And you use the true labels, you use the test scores. the scores for the test cases, and it gives you 0.968. The best case is 1, right? And 9.968 is not that bad. And we want to do some comparison, right? There's no comparison at all. So we want to compare the logistic regression with another classifier. So we'll build a classifier called random forest. So we'll talk about this in a few weeks. So to build the random forest classifier, we simply import random forest classifier. We did it in the first cell. And we also set the random state so we can reproduce the outputs. We call the classifier forest classifier. And we fit the data, same as what we did. And then after we fit the data, we get the scores. The scores are simply the probabilities, right? Like the logistic regression, you can get the probability, sigma of beta transpose x. Right here, we can do something similar. We can get the probability of each case. So we do a predict probability for the test case, and we get the probabilities. We call it Y probabilities forest. And these probabilities later will be used as scores. Right, so we take the second column of the probability. So that's the probability for positive class. The first one is for negative class. But remember, we did it for the logistic regression. We have two numbers each row, right? One is, for example, 0.4, the other one is 0.6. So their sum is equal to 1. So we do some similar things here. So the test scores are simply the probability for the positive class. So we take the second column. And now we get the ROC curve. That's pretty much the same as what we did before. We need the true labels. We need the test scores, right? And we get the FPR, TPR, and thresholds. Later, we'll see the use of the thresholds here, right? We can actually get thresholds to use to build all of this FPR and TPR. And make a plot of FPR for the forest case, and we actually get the red line here. We plot again the logistic regression case. That's the blue line here. So you can see the red line. It's more close to the top left corner. That means it's better compared to the logistic regression. And actually for the AUC, we get 0.999. That's really close to 1. So this also means it's better than the logistic regression. All right, so the last part, we want to talk about another curve. So the curve we just talk about is ROC curve. That's the precision, it's the recall versus the false positive rate, or true positive rate versus false positive rate. We can also make a direct plot of precision against the recall. Right, so we talk about the trade-off of precision and recall. What we can do is simply we just use the precision and the recall. It also tells us something. And it's very similar to ROC, and the usage is also pretty much similar. All right, so let's see how we can get the get a plot of precision versus recall. So what we first do is let's use the logistic regression, and we get the scores. Right? So we call it decision function for the test cases. We get the scores, and then we can get the precision and the recalls. Again, it's related to multiple thresholds, like the ROC curve. Each point on the ROC curve corresponds to a certain threshold. Same thing here. We want to make a plot of precision versus recalls. We need to consider different thresholds. One threshold gives us a precision and a recall. Right? So we'll consider different thresholds. So that's why we need to first to get the scores, and based on the scores and the true labels, similar to the ROC curve, we can call the precision recall curve. Imported from the same package. It gives us three things, right, similar to ROC. For ROC, we get FPR, TPR, and thresholds. Here we get precision, recall, and thresholds. right? Then we make a plot of the precision only against the thresholds. So we can see something, the blue line here. So as we can see here, the precision against the thresholds. As we increase the thresholds, we mentioned before, precision will increase and the recall will decrease. Right? So this plot actually also tells us the same thing. And we reduce the threshold, right? The precision will decrease, recall will increase. That's the same thing as we talked before. And how to make a precision recall curve, that means precision versus recall. So we simply plot X recalls, Y precisions. And how to use this curve, right? To use this curve, we can look at this is the prototype of how to use this. This is very similar to ROC curve. The best case or the perfect classifier is this purple line here, right? Similar to the ROC curve, the best one is vertical, then horizontal. Same thing here, the perfect classifier is the purple line. So good classifier is just not, it's not the same as the perfect classifier, but it's not too far away, right? Then if you have another classifier, it's like this, then it's better than the pretty good classifier because it's more to the top right corner. The more to the top right corner, the better the model is. And this is a baseline classifier. This is like the y equal to x line for the ROC curve. Right, so we'll try to understand what this means for perfect classifier, baseline classifier, and just a regular model. Right, so this is very similar as we try to understand in the ROC curve. So look at the perfect classifier. So we use the same plots. Right, so this is a model that the classifier that can completely separate the two cases. There's a true negative, right? This is a true positive. Negative cases, positive cases. So if the threshold is here, let's see what happens. If the threshold is here, what's the recall? The recall is 1 because it captures all of the positive cases. Right? And then we see, so the recall is here, it's equal to 1. And we see what's the precision is. For the precision, it's actually 0.5 in this case. Right? Because if the threshold is here, it predicts this 100 case as positive. It predicts this 100 cases as positive. So for precision, remember the definition is true positive over true positive plus false positive. Or the denominator simply the cases that are predicted positive. So true positive in this case is 100. Right? Suppose the area under this curve is 100. It's also 100. Then we have 100 plus 100. So it's 200, it's 0.5. So it gets this point here. And then we move our threshold to here. What we get is recall still 1. And the precision is 100 divided by 100 plus 50. Right? So when it moves here to the right, the points will move along this vertical line. Right? Until we get this threshold here, again, recall still 1. And in this case, our precision is 1 because all of the 100 cases, they're predicted as positive. But they're truly positive. There's no false positive. So it's 1. So we get these points. Then we move to here. Now the recall is no longer 1 in this case is actually 0.5. And the precision is actually 1. All of the 50 cases that are predicted positive, they are truly positive. So it's 1. So to be a point here until we get here, right? That's the point here. So to move move along the vertical line first and along the horizontal line. Right, so this is the perfect classifier. And what's a baseline classifier? Baseline classifier is the case we just talked about where you have random classifier. Right, suppose both of them are totally overlapped. So in this case, let's look at different cases for the threshold. The threshold is here, and the recall is 1 because it captures all of the positive cases. Right? So, and the precision is 0.5. Right? Half of the cases are false positive. Right? So we have 100 over 200. So that's 0.5. So we have 1.5. That's this point here. And then we move to, let's say, move to the middle. In this case, the recall is 0.5 because we only captured half of the positive cases. And what's the precision? The precision is also 0.5 because you have 50, true positive is 50 cases, and false positive is the blue curve. Under the blue curve, that's also 50 cases. So it's 50 over 100. So that's 0.5. So I have point here. And move here, you will move here. So to move along this horizontal line, which is y equal to 0.5. So that's the baseline classifier. Right? So as you get a better model, then the random classifier, you will move up, right? Move up this curve. And the best case is here. So this is an even better model. So the more close to the top right corner, the better the model is by using this precision recall curve. And also we can find the area under the precision recall curve. Just to call this AUC function, import it from the same metric, use the recalls and precision. It will give you the AUC number, that's 0.88. If you use another classifier, you get a higher precision recall curve, and that means that that model is better. But you cannot compare the precision recall AUC with the ROC AUC, right? They're totally two different categories. So you have to compare apples with apples, and that makes sense. So then you may wonder, when should we use ROC curve or when should we use precision recall curves to compare models? Right? So the rule of thumb here is if ROC curves, if you have roughly equal numbers of observations, that's balanced data sets, then you should use ROC curve. If you have a skewed data sets, right, then it's better to use precision recall curves. The comparison give you more confidence if you in that case. Right? That's a rule of thumb. And the final thing I would like to talk about the precision recall curve is like the threshold selection or the model selection. So same thing as we talked about the ROC curve, right? You can use the precision versus recall curve to maybe to select a model. This is precision. Right. Suppose you have you are more you care about precision more. Right. Or let's do it this way. This is better. Let's see if you care about recall more. Right. For example, for the cancer detection case. Right, you want to have a higher recall. Then how to just to look at the precision recall curve, then what's the best threshold you should pick? You want to get a higher recall. So, for example, this is a point that you should consider. And why? Because after that, you actually increased your recall, but you can see the precision dropped sharply. Right? Again, when you're trying to get a higher recall, you don't want to have a very low precision. So in this case, this point can be used as the threshold. So you can find the threshold corresponding to this point. Right? You have all the thresholds actually from the codes you just called. Right? You have all the thresholds. Look at the approximate value of this threshold. Use that threshold as your model, which will give you a pretty high recall, but also a relatively high precision. You don't want to pick this one, although the recall is higher, but the precision is much lower. You also don't want to have a point here because the precision doesn't increase much, but the recall is significantly reduced compared to this point. So you can also use the plot of precision recall to select a good threshold so that you get a better model that better fits your need. All right, that's all for lecture 5.